Hello, Shake Ambassador Club students, T3 Seismic Studies students. Today we have a really exciting lesson. I'm excited to talk about this, which is seismic monitoring. And that is what our course is about. That's what our whole thing is. Seismic, right? Ground motion, seismology, study of ground motion, seismograph, seismometer, all these things measure motion and ground motion. So here we go. Let's kind of look into this. What is seismic monitoring? So first, I want to kind of give a bigger view on just environmental monitoring. And environmental monitoring could be all sorts of things. It's just looking and noticing the world around us, right? And especially when you think of environmental monitoring, a good way to kind of narrow it down, because environmental monitoring could be, I go out and do some testing of the water with some strips to learn about the pH or looking for different chemicals here. But what we're talking about is time series geophysics environmental monitoring, which that's a really fancy word to mean geophysics is like, earth processes, like ground motion, like weather is geophysics too. Is that kind of geoscience. So time series is over time. And you see these few photos, like this one here, you see a wind sensor, air temperature, humidity sensors, rain gauge, pressure sensor. Down here, there are some seismographs being installed, right? Ground motion sensors. That's monitoring your environment, changes in your environment over time. What that looks like, it ends up looking like a graph that moves over time. So this first graph is just, a seismogram or a ground motion graph that just shows how wiggly the ground is, right? Which, oh, look, it's flat, it's flat, it's flat. Oh, boom, 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 boom. That's an earthquake. We'll learn more about how to recognize it later. This is a temperature over time graph, which is basically the same, same kind of thing. It's like, okay, what are the changes over time? And you can put different time series, data next to each other. And that is a great way to learn about what's going on around us. We can better, adapt to our environment. Because that's really what we as kind of humans and animals like to do. Everybody does is adapt to their environments. And what this field of study does, time series geophysics environmental monitoring helps us to do that better. And especially when looking at seismicity. Why do we monitor seismicity? Ground motion. It helps us gain understanding of what's going on. How does this work? How does ground motion, what are earthquakes, what are the other things that make ground motion shaking? Detect events so that when events do happen, we know how they happened, why they happened. Sometimes you can even detect them immediately when they happen and actually have a early warning of a few seconds, and that can really help people. And then, better prepare and adapt. Prepare for events that might be kind of bad. I mean, it's seismicity is, with earthquakes and volcanoes and tsunamis and such. But if you think about weather and learning how to monitor weather so that we can prepare for storms, right? It's all about preparing and adapting. You can also monitor seismicity to see what other, to see non-natural things like explosions. You can notice, like when North Korea did some nuclear tests, you could see the nuclear tests. The reason we know about them is because of seismographs. It's because of seismic monitoring, right? So how does this work? So the measurement of seismicity is done with seismometers, right? Most data will be recorded with a suspended mass attached to a fixed base. When the Earth shakes, the base moves, and the mass does not, right? And you can see that in this image here, and I'll show you a bigger one in a second. Seismographs not only measure earthquakes, all ground vibrations are heard by the sensors, traffic, thunder, construction. Anything that you feel shake is definitely going to be recorded by something like this. But even the ones that don't, you can't feel, like an earthquake that happens around the world on the other side of the world can be detected on a well-installed seismic, seismometer. And you might be wondering, like, okay, what's the difference between seismometer and seismograph and seismogram? Those three ones are really weird. So basically seismo is the root word, which is, earth motion, and then seismometer is to measure. So seismometer is earth motion measurement. So that's anything that measures it. Seismograph, graph is to record, right? So you think about like graphing something, it's kind of recording. So seismographs measure and record. So usually a seismograph includes some sort of system to not only sense the data, but also kind of process that data and record it and save it. And then seismogram, the gram is just the plate, like but I'm not sure what exactly that means, but the root word is, but it's just the graph, the waveform, like the result, All right. So here's a bigger picture of what this is. And I want everyone to look at this as you're watching the video and kind of see, okay, there is the suspended mass that stays in the same place while the Earth moves around it, right? So watch this closely. So see how this is like an earthquake. There's a P wave and an S wave we'll talk about. So boom. Yep. P wave and then S wave, right? And see how the mass stays still and the ground actually moves around it. And that's how they work. And there can be, seismographs that are not vertical. There can be seismographs that are horizontal, and they work very similarly instead of up and down, left to right, but it's similar kind of thing. Okay, so how did this start? I mean, how did seismograph, seismogram, seismometer start? And really, the first thing here is this is actually what they call a seismoscope. And it was invented in China a long time ago, probably thousands of years ago. And it was, they had earthquakes in China. They were like, whoa, where is this coming from? Where is it? Because in China, they had like a whole, government and, emperors, and they needed to know where these big damaging events happen so they could go maybe help. And what this was is a vase that had these dragons, these heads that had little balls that were in the mouths. And when an earthquake came by, right, boom, a P wave came, boom, and shook it. Usually it shakes in a certain direction. And you could tell that where the mouth spit out the, if the ball fell out of the mouth, you could tell that, oh, now I know which direction it's coming from. And you could kind of you could send people to that city and figure it out. So they were thinking about earthquakes and trying to understand where they're coming from, and what they were doing a long time ago. So, much more recent, this started only, a few hundred years ago now, or less than 100 years ago, was the paper seismograph, right? And that included this big rotating drum and a weight and a pen that would, work just like this one we see here. And these were in use for I think like 100 years, or maybe a little less than 100 years. But they were in use for a very long time. And actually in Alaska, we had one of these up until very recently, only in the 80s, I think, or maybe even 90s they came out. And I'll look that information up and let you guys know the exact dates. But this is maybe what you think about when you used to think of, okay, seismographs. So now, how does everything work? They are all digital. And, they're all with very specific sensors and how things move up and down. So there are a few different types nowadays. There are broadband seismometers, and they are these big tubes. And you see this, like this one here in the middle. There's big tubes, and inside there are some super delicate, super sensitive electronics that can tell when just, there's the tiniest bit of movement up and down, or left and right. And they have all three axes. They have north, south, east, west, and then up and down. So they're very sensitive. They can be maxed out. So if there's a giant earthquake where it just shakes, the whole thing, then they'll get maxed out. What's called clipping. The sensors will clip. And, these sensors are very expensive to install, very expensive to buy, and it's they're used by the professional sensors because they're the professional, Alaska Earthquake Center uses these. We use these because they are the best. They're the best data, kind of top of the line. And you can detect the most earthquakes and get the most data out of it. So what else is there? There are strong motion sensors. So actually in this last photo you can see here, I'm pretty sure this is a strong motion sensor right next to this big fancy sensor. And what the strong motion sensor does instead is it's actually an accelerometer. So instead of these little suspended masses, right? Like here, it's kind of like a big version of this where, it can only go so much up or down before it just, it hits the top of the cylinder, right? Whereas accelerometers, what they do, and this image shouldn't be here, just ignore that, sorry. What the strong motion sensors, actually, maybe it could because the Raspberry Shake 4D does have accelerometers. But like this sensor in Etna 2, what they have, accelerometers are the same things that are like in your phone. That let your phone know how fast it's going, or if it like moves really fast, like this way or that way. They're also in cars. What these accelerometers do is they just have little bits of electronics in there that can tell when it's moving and kind of how fast it's moving, but it's not as sensitive. And why these sorts of sensors are good for seismic monitoring is if there's a giant shake, like, what could happen in Alaska in a lot of places where it's like, whoa, you can't stand up and it's moving really big, then accelerometers can capture that motion really well. And they won't ever max out, right? So they're less sensitive, but they don't clip or max out. And this Raspberry Shake is actually the Raspberry Shake 1D, which doesn't have accelerometers. It just has a geophone, which I'll show in a second. But the 4D, which many of you have in your schools, does get strong motion, which is good, especially when there are big earthquakes. All right, so short period geophones. So these are like miniature broadband sensors a little bit. They just have one direction. So you can see these are what are in our Raspberry Shake. So they're small, cheap, and sensitive, and often used they're actually developed and used for oil and gas exploration, because one of the ways that they look for oil and gas underground is they put a whole bunch of these little geophones on the ground in a line or in like some sort of array, and it's like some sort of pattern, right? And then use big trucks to go boom, boom, and thump the ground. And the way that the energy waves go down and then bounce off of whatever's underneath the ground and bounce back up, they can actually tell if there's oil and gas under there. And so that's why these geophones are used for that. And I can go more in detail if you want to know more about that too. So these are the sensors that are used in the Raspberry Shake. And like this picture of the 3D, which many of you have in your schools, it shows that there's one vertical component, up and down. There's one horizontal, probably going, north and south, and there's another horizontal going east and west. And inside of there, right, is the same kind of thing as we saw way over here. There's some inertial mass that stays in there that while the rest of it moves, it stays still. And you can see that here. There's the inertial mass. In there's a magnet, and actually it's the electromagnets, because there's a coil around a magnet, which if you have learned about electricity generation, that's how a lot of generators and alternators work, is just moving around the magnet past a coil. So that creates a little electricity, and then that's how that becomes data. All right, so Alaska Seismic Network, especially the Alaska Earthquake Center's network, is mostly broadband sensors all around the state, and especially around some of the regions that have more earthquakes or more volcanoes or more activity. That's interesting. As you can see, there's less density over in the northwest and western regions. That's also because there's less seismicity there. The hobbyist Raspberry Shake network, right? And that's a separate seismic network that is completely like hobbyists, people who really like earthquake or really like seismology, can just buy a Raspberry Shake and have them in their houses. A lot of schools have them, and that's what we have in our seismology schools, our Shake Ambassador Club in this course, and that's what we're going to be learning about. And I'll talk more about why seismic networks are important as we go forward, and what they do and how you locate an earthquake and all of those things. But right now, let's talk about this guy, the Raspberry Shake seismograph. Many of you, hopefully all of you, have this seismograph. And if if either it's installed or you're working on installing it, if not, let me know immediately. If you watch this and you're like, wait a second, I don't have one of these, then let's figure that out. So how does this guy work? Well, as we already talked about, the sensor, the thing that actually gets the data, is that geophone. And if you hold the Raspberry Shake and shake, you can actually kind of like feel it. So from there, that data goes into what's called the digitizer, which is the little blue thing on top of the Raspberry Pi, and you see in there. And that takes that analog data and turns it into numbers and ones and zeros that the computer can read and processes that data. And then the computer, the Raspberry Pi, connects it up to the then be a part of, be able to connect to it, have the local browser, web interface where you can program it, and then sends it to the global network, which we'll explore here in a second. But that's kind of where you can go in and access the data. So with the Raspberry Shake, right, you can detect earthquakes, all these tremors. You can detect all sorts of things other than earthquakes, and that's what I really want to highlight for you guys. You can detect landslides. If your community has landslides, that's how most landslides that aren't in areas where people live are detected, is actually because of seismographs, and your Raspberry Shake can do that. Water movement, volcanoes, sinkholes. You can detect all sorts of things: fracking, explosions, nuclear testing, wastewater injection, demolition. Any of these things, you can actually detect whatever is vibrating. If there's some construction going on, you can detect that. You can detect traffic, footsteps, washing machines, and I'll go into that a little bit here in a second. But what I want to get across is, with these tools, with these seismograph tools, you can detect all sorts of things. And there are all sorts of different kinds of seismographs. What you guys are worried about is just the one you have, which is that Raspberry Shake seismograph. So what are the types of seismic data? Actually, I'm going to end this video here and start one more video talking about the types of seismic data, because it's been a little bit of a long video. So thanks. I'll see you in the next video.